the turbine rotor. The turbine stator consists of the following parts: the turbine shell, the shrouds, the nozzles. The turbine shell function is to control the radial and axial positions of the shrouds and the nozzles, and the relative clearances between the nozzles and the rotating buckets. The position of these parts is critical to the turbine performance. The lower half features two trunnions used with other trunnions on the forward compressor casing to lift the gas turbine to or off the turbine base. The external surface of the turbine shell incorporates cooling passages. Unlike the compressor blades, the turbine rotating bucket tips don't run directly against the stator casing, but against curved segments called the shrouds. The primary function of the shroud is to minimize the tip leakage. These shrouds are attached to the turbine shell by sliding onto the T-hook arrangement machined on the turbine shell. Joints between first stage shrouds are sealed by cloth seals. Shrouds are maintained in the circumferential position by radial pins from the turbine shell. The first stage shroud is coated with thermal barrier coating to withstand the extremely high temperatures at this stage. The second and third stage shrouds have teeth that mate with teeth on the tip of the second and third stage buckets. This labyrinth seal minimizes tip leakage. For better tip clearance, a honeycomb seal is integrated on the second and third stage shrouds. This honeycomb is relatively soft material. The cutter teeth on the tip of the second and the third stage buckets open a slot on the honeycomb seal without any material transferred, providing tighter clearances to improve the unit efficiency. Shrouds of the last two stages are sealed by interconnecting tongues and grooves and by key seals. In the first stage nozzles, hot gases received from the combustion system are expanded and directed to the first stage rotor buckets. The first stage nozzle consists of 18 cast nozzle segments. Each segment contains two airfoil partitions. These partitions are hollow. This permits the relatively cool compressor discharge air to cool the nozzle segments by entering from the impingement plates and exiting through holes on the trailing edge into the hot gas path. The 18 segments are contained on a horizontally split retaining ring. The retaining ring is supported to the lower turbine shell by two lugs extruding from the lower retaining ring half and held in place by clamps. The retaining ring is centered by two eccentric pins from the turbine shell. This configuration permits radial expansion due to the high temperatures encountered, while the ring remains centered to the shell. The aft outer face of the retaining ring is loaded against the forward face of the first stage shroud, with steel strips in between to prevent compressor discharge air leakage between the nozzle and the shell. The nozzle one assembly is prevented from moving forward by four lugs extruding from the outside diameter of the retaining ring at 45 degrees from vertical and horizontal center lines. These lugs fit in a groove machined on the turbine shell. On the inner sidewall, the nozzle is sealed and supported by direct bearing of the nozzle inner load rail against the first stage nozzle support ring. The first stage nozzle support ring is mounted on the aft face of the compressor discharge inner cylinder. Hot gases leaving the first stage rotating buckets are expanded again and directed to the second stage rotating buckets by the second stage nozzle. The second stage nozzle set consists of 16 segments. Each segment contains 3 airfoil partitions. The nozzle segments are assembled by fitting the male hooks on the forward and aft sides of the outer sidewall into the female groove on the aft side of the first stage shroud and on the groove on the forward side of the second stage shroud. Seals are installed between the segments to minimize leakage. The nozzle segments are held on the circumferential position by radial pins from the turbine shell into axial slots on the nozzle outer sidewalls. Annular curved segments are attached to the inner sidewall of the nozzle. These segments are called the diaphragms. Each diaphragm is secured to the nozzle by a pin. These diaphragm segments prevent hot gases leakage past the inner sidewall of the nozzle and the rotor. A high-low labyrinth seal is machined on the diaphragm inside diameter. These seals mate with opposite sealing lands on the turbine rotor spacer. The second stage nozzle is cooled by compressor discharge air passing through the first stage shroud. Some of this air exits through holes on the airfoil's trailing edges. The remainder of the cooling air is directed to the first stage aft wheel space through 3 cooling air tubes assembled on the diaphragm. A brush seal segment is installed on the inside diameter of the diaphragm between the labyrinth seals. This brush seal is in continuous contact with the turbine rotor spacer surface to control the amount of the cooling air passing from the first stage aft wheel space to the second stage forward wheel space. This ensures more precise cooling and better unit efficiency. The third stage nozzle receives the hot gases from the second stage rotor buckets, expands it further, and directs this flow to the third stage rotor buckets. The third stage nozzle set consists of 16 segments. Each segment contains 4 airfoil partitions. A diaphragm segment is also attached to the inner sidewall of the nozzle. The third stage nozzles are not air-cooled. These segments are installed to the stator in the same manner of the second stage nozzle. The third stage nozzle is supported by the second and third stage shrouds. The nozzle segments are held on the circumferential position by radial pins from the turbine shell into axial slots on the nozzle outer sidewalls. The turbine rotor consists of the forward wheel shaft, first, second, and third stage turbine wheels, 2 turbine wheel spacers, the aft wheel shaft. All parts are assembled together by 12 studs. The forward wheel shaft is machined to provide the following features: journal surface for bearing number 2, and surfaces for oil and air seals. Forward balancing groove. Forward flange to connect the turbine rotor to the compressor rotor. The forward wheel shaft is hollow to pass the turbine rotor cooling air. The first wheel carries the 92 buckets of the first turbine stage. Like the next 2 stages, buckets could be disassembled without rotor removal. Being the first part then encountered by the hot gases leaving the first stage nozzles, these buckets are protected by thermal barrier coating from outside and air-cooled from inside. When the bucket is attached to the wheel, a small air plenum is formed in between. The rotor internal cooling air, which passes through slots on the forward face of the first wheel spacer, is fed into these plenums. Cooling airflow from this plenum to a series of longitudinal air passages to cool the bucket and exit at the recessed bucket tip. Buckets are attached to the wheel by straight axial entry multiple tang dovetails that fit into matching cutouts on the wheel rims. The buckets are prevented from moving axially by the D-key arrangement. A radial locking pin is installed before the first bucket. Then, the first bucket is installed and locked in place by the D-key. This is repeated for the next 90 buckets. The last bucket is installed and an axial locking pin is inserted on the locking bucket dovetail. This pin pushes the radial locking pin to hold the last bucket on position. The first wheel spacer is located between the first and second turbine wheels. Spacer function is to define the axial position of the turbine wheels. The outer diameter of the spacer carries the diaphragm sealing lands. Slots are machined on both forward and aft faces for cooling functions. The second wheel carries the buckets of the second turbine stage. 92 buckets are also installed on the second wheel. Buckets are attached to the wheel by the same dovetail arrangement of the first stage, but they are held on the axial direction by twist locks arrangement. Twist locks are first placed on the wheel. Then buckets are installed as a 360 degrees ring due to the interlocking between the buckets. Once the buckets become on position, the twist locks are rotated and stacked. Buckets are internally cooled by the rotor internal cooling air, which passes through slots on the aft face of the first wheel spacer. This air is fed into a plenum casted on the bucket shank. From this plenum, air flows into span-wise holes machined on the bucket and exits at the bucket tip. The second stage bucket tip is enclosed by a shroud, which is a part of the tip seal. These shrouds interlock from bucket to provide vibration damping. These shrouds also feature the cutter teeth, which open slot on the honeycomb seal and mates with the seals on the shroud block. The second wheel spacer is located between the second and third turbine wheels. Slots are machined on the forward face. The forward face of the spacer is machined to form a gap at the mating surface with the second stage wheel for cooling functions. The third wheel carries the buckets of the third turbine stage. 92 buckets are also installed on the third wheel. Third stage buckets are not internally cooled. Third stage bucket tip is also enclosed by a shroud. Buckets are attached to the wheel by the dovetail arrangement and held on the axial direction by twist locks arrangement like the second stage. The aft wheel shaft is machined to provide the following features: journal surface for bearing number 3 and surfaces for oil and air seals. Aft balancing groove. Aft flange to connect the turbine rotor to the generator rotor. The turbine rotor must be maintained at reasonable operating temperature to assure a longer turbine service life. For this purpose, bucket vanes are not directly attached to the dovetail. Instead, they are connected to their dovetails by means of shanks. These shanks locate the bucket to wheel attachment at a significant distance from the hot gases. Combined with the diaphragm segments, this arrangement isolates the rotor away from the hot gases flow. Seals from the first stage nozzle support ring mate with sealing wings extruding from the forward side of the first stage bucket shank. Also, seals from both sides of each diaphragm mate with sealing wings from both sides of each bucket. The seal from the exhaust frame mates with the sealing wing on the aft side of the third stage bucket shank. All these seals reduce leakage of the hot gases radially inward to rotor parts, improving turbine efficiency and protecting the rotor parts. The rotor parts are cooled by positive flow of cooling air discharged radially outward through a space between the turbine wheels and the turbine stator parts. These spaces are called the wheel space. The first stage forward wheel space is cooled by compressed air leaking from the high-pressure packing at the forward end of the inner barrel. The first stage aft wheel space is cooled by the compressor discharge air supplied through the second stage nozzle. The second stage forward wheel space is cooled by a portion of the first stage aft wheel space cooling air, which passes through the labyrinth and brush seal. The second stage aft wheel space is cooled by the rotor internal cooling air, which passes through the slots on the forward face of the second wheel spacer. The third stage forward wheel space is cooled by a portion of the second stage aft wheel space cooling air, which passes through the labyrinth seal. The third stage aft wheel space obtains the cooling air from the exhaust frame cooling system. The rotor internal extraction cooling air is utilized for bucket and wheel space cooling. This airflow also maintains the parts of the rotor at approximately compressor discharge temperature. This ensures longer service life for turbine rotor parts. For efficient gas turbine operation, clearances between all rotating and stator parts should be tight as possible. As the turbine shell controls the radial and axial position of all turbine stator parts, the shell should be isolated from the high temperature of the enclosed hot gases. This will ensure the control of the shell diameter and roundness to be maintained. The heat transfer from hot gases is reduced by the following means. Hollow shroud blocks provide high thermal resistance between the hot gases and the turbine shell. The first stage shrouds are cooled by the compressor discharge air. The third stage shrouds are cooled by cooling air from the cooling and sealing system. This air is extracted from the compressor fifth stage and supplied to the third stage shrouds through 6 holes machined on the turbine shell. Combined with the assembly of the nozzles between shrouds, hot gases are kept away from the shell. Heat transfer from the nozzle segments to the shell is reduced by means of insulation packages. The external surface of the turbine shell incorporates cooling air passages. Cooling air is supplied from the exhaust frame cooling circuit. To control the amount of airflow, multiple metering orifices are installed on the flow passages.